So I'm going to talk about some work that I've been engaged in with Ed Dlugo-Kensky here at NOAA as a role in Boulder. And what I'm going to talk about is the state of our knowledge about the atmospheric budget of methane in the Arctic. And I want to start out by showing one of our products that we have here at NOAA GMD. It's called the Annual Greenhouse Gas Index. And it's entirely based on observations of trace species that we make using our global network. And we calculate the contribution of different greenhouse gases that have significant anthropogenic components to their budgets. And we ask ourselves, how has the forcing of the climate changed over time as emissions have gone up? And this figure shows very clearly that when it comes to radiative forcing, CO2 is really the big story. But the second largest contributor is methane. So we definitely want to understand methane and understand its budget and how its emissions may be changing over time. An interesting thing about methane is that when it comes to the Arctic, methane is quite a climate-forcing bogeyman. There are several processes that have received a lot of attention that allege that there could be huge climate feedbacks coming from changes in methane emissions, especially in the Arctic. And here I have a slide describing the permafrost carbon feedback. I'm not going to discuss the potential release of large amounts of methane from ocean hydrates, but that is another issue that people have looked at. In terms of the permafrost carbon feedback, there was an excellent review article that appeared last year by Ted Schur et al. And there are some revised estimates of how much carbon really is thought to be locked up in frozen Arctic soils. And it's quite a huge amount, 1,300 to almost 1,600 petagrams of carbon. Estimates are that 5 to 15% of this could become vulnerable to being emitted to the atmosphere as greenhouse gases, CO2 and methane during the century. But the current thinking is that this release will be gradual. It'll occur over multiple centuries rather than being a sudden catastrophic burst, which leads us to understand that if somehow the global society is able to get their act together and control emissions of carbon and keep the global temperature increase to less than about 2 degrees, perhaps we'll escape the worst effects of the carbon permafrost feedback. So now, the thing about methane is we don't really understand the global methane budget very much. There's many different versions of the global methane budget. I'm showing you this one because I happen to think it's really kind of an artistic representation. But you'll find some budgets that evenly split emissions between natural sources and anthropogenic sources. This one happens to have a little bit larger natural sources than anthropogenic. But it's really difficult for us to divide up this pie into different emission processes because, well, a lot of the emissions are very spatially overlapping or very diffuse. It turns out to be pretty hard to get a good handle on how this pie gets divvied up. Recently, global methane observations have shown that methane, after appearing to level off in the late 1990s and early 2000s, is now on the rise again. And at first, of course, we were hoping that maybe it would be just natural variability. Maybe we just had an extremely warm and wet year, especially in the tropics where most of the emissions are in the end. But no, it's sustained and it's continuing to rise. So an important question, of course, is what is driving this recent growth? Is it anthropogenic or natural? And in terms of this question, many things have been proposed. Some people have suggested that the Arctic is actually responsible. Others have suggested that it's related to the explosion in North America. And others have suggested that perhaps it's some sort of climate feedback related to natural wetlands becoming more productive over time. One place we can look to get for clues on this is associated tracers. So if we look at the C13 isotope of methane, we can get a handle on how much of global methane increase might actually be coming from microbial sources versus fossil fuel sources versus fires. So these processes have broadly different fractionations, different isotopic signatures. And so when we look at the global isotope information, and this was done recently in a paper by Schaefer et al., appeared in Science, the isotopic information suggests that most of the recent increase is likely to be microbial and probably not in the Arctic. On the other hand, there have been a flurry of papers recently that ignore this information and suggest that really it's oil and gas that's contributing to this rise. So, it remains to be seen. I myself find the isotopic information pretty compelling. There's another paper about to hit Nature on October 6th that reinforces this view. And you might wonder, why would I say that it's likely to be non-Arctic? Well, it turns out that we can sometimes learn something about the spatial distribution of sources from our global network information and from the way things vary spatially. And one way we have of trying to estimate global emissions is by using the top-down approach, which in essence is to use atmospheric observations, which integrate the signals of emissions throughout large scales. And so I'm going to describe to you how the top-down approach, i.e. atmospheric observations, can be used to estimate emissions from different regions and from different sources. And the way it works, and another word for this, of course, is atmospheric assimilations or atmospheric inversions. But the way this works is very similar to what we do when we forecast the weather. We use a model and we combine the model with observations to produce the most consistent estimate of the forcings that we can come up with. So this figure here from the recent AMAP report on methane, Arctic methane, kind of shows you a schematic of how it works. You start with your best guess of what the underlying emissions are, and these are called prior fluxes. In the case of methane, you have to account for chemical losses in the global atmosphere. You use an atmospheric chemical transport model to simulate methane abundance at different observation sites where you have measurements. And in this case, I have a map of our current atmospheric network. And then you use a numerical optimization technique to figure out how you need to change your first guesses in order to obtain optimal agreement with your observations. So that's how you come up with a new guess for the underlying emissions. In essence, this whole scheme is playing off of the spatial gradients that we get from our network observations. So what I'm showing you here is the growth rate of methane as a function of latitude from our atmospheric network. And you can see that there's information in here potentially about what sort of methane sources are varying and where they're varying. So you see a lot of variability in the tropics. There's times when the growth rate in the tropics is really increasing rapidly and times when it's decreasing. And likewise, if you look at a year like 2007, when we know it was really warm and wet in the Arctic, you see that the growth rate was unusually large there. So it's this kind of observational information that atmospheric or inversions are using to get information about the fluxes of methane and how they're varying over time. So it turns out there's quite a lot of us doing these kind of calculations all over the world. And recently, as part of the AMAP report, we took a look at results that various groups are producing, and we compared them. And so here you can see, I'm not going to bore you with which inversions are from which group, but you can see that there's not a whole lot of agreement on the north-south distribution of methane emissions. And these groups are using, different first guesses. They're using different transport models. Different data. Some of them are using space-based column average methane, some are not. So you can see here that although we know the general way methane emissions vary with latitude, we don't really agree very well ultimately on the distribution of the emissions. Now the blue box in the high latitudes is what I want to focus on for the rest of this talk. because what I want to talk about is how do we know what the budget of Arctic methane emissions are? And if we use one of these top-down atmospheric observation approaches, does that agree with what we learn when we go out in the field and measure fluxes directly? So when we go out in the field and measure fluxes directly, that's called the bottom-up approach. And so I've compiled in the table here some fairly recent studies which use field measurements to and scale them up for the whole Arctic, and try to estimate what is the total effect of these processes. So there was a study by McGuire et al., a recap study in 2012 that looked at flux measurements spanning several decades, and they figure that 26 teragrams of methane per year are coming from the tundra wetlands. Then a while ago, there was this, actually it's not in press anymore, it came out in 2015, I believe, but there was this excellent paper by Martin Vick et al., and they took a close look at high northern lakes, and they found that aggregate-wise that there could be 17 teragrams coming out of those. Then you have the ocean hydrate, the anomalous hydrate, papers by Shachova et al., and you could add on another 17 there. And then recently there was some interesting work about cold season emissions, and then there's the freeze-out emissions by Stepanov. And I'll bet you if I continue to peruse literature, I could find more estimates where bottom-up information has been scaled up to get a pan-Arctic budget. If you add all this up, you get about 76 teragrams of methane per year, with quite a large uncertainty. And let me just note here that we think the global budget of methane, the global emissions, are probably in the vicinity of 550 teragrams per year or so. So now, how does this agree with the top-down picture? Well, if you look at all those inversions I showed earlier, and you look at what they say about the Arctic latitudes, you come up with a much smaller estimate of how much emissions can really exist in the Arctic. So the atmospheric observations are suggesting that you can actually fit about 25 teragrams per year versus the bottom-up estimates, which are almost 80. So that's quite a large discrepancy. Another important thing we might want to do with these inversions is ask ourselves whether we see any trends. And the problem is that we don't have a long enough time series at this point to really be sure. But at the moment, the inversions don't agree very well, even on interannual variability. You can see that in 2007, many of the inversions, if you look at the bottom figure, which are emission anomalies, you can see that many inversions agree that that year was a higher than normal emission year. On the other hand, at least some of the inversions are saying it was a normal year in terms of emissions. So we have quite a ways to go, I think, before these calculations can really give us robust ideas about variability and trends. So an interesting question is, why do the top-down and bottom-up approaches disagree? And there are many reasons for this. Let me pick on the inversions first. One problem we have is that inversions, it's very difficult to simulate continental sites. And just as an example of this, I want to draw your attention to the figure over on the left. This is a time series from different air sampling sites throughout the Arctic. And the black line that corresponds to Alert Canada is what we would call a background site, which should be measuring the well-mixed Arctic background atmosphere. And you can see that this reflects a seasonal cycle where you have a minimum in the summertime that's there basically because that's when the global chemical loss is, or when the chemical loss is fastest in the northern hemisphere. So you get a minimum there, even though we know that's when Arctic sources, natural sources, are likely to be pumping out most of their methane during the growing season. But if you go and measure near wetlands, for example, at Inuvik, Canada, Chersky, Russia, Cholat in Canada, those places, then you see that the seasonal cycle looks very different. You can often get a late season peak in methane concentration. So the problem is when we do these inversions, we have a hard time correctly simulating the transport and mixing at continental sites. We cannot make use of this data, which means we are not informing our flux estimates with this very useful data that's near sources. So we need to change that. We need to go to better and higher resolution transport models, and work really hard to improve how well we're able to represent situations at these sites. Now, in terms of the bottom-up approach, one problem is that there may be spatial biases in where we collect the bottom-up information. You know, of course, we all want to go where the interesting stuff has happened. So maybe we're sampling often near very active places where methane is being produced, and maybe we're not getting a good picture of what happens throughout the whole Arctic. And this leads me to my third point, and that is that it's really very difficult to scale process-based observations from flux towers and things like that, and chambers. It's very hard to scale that up to the entire Arctic. And perhaps someday, you know, space-based data will help us learn how to do that in some way. So now I have a few more slides, and the last thing I want to talk about is some more recent work, give you an overview of what people are thinking about right now. Of course, the big question is, even though the prevailing wisdom now is that the permafrost carbon feedback is going to be slow and take centuries, you know, even the Arctic is warming very rapidly, and so even the existing wetland systems up there have the potential to put out more methane than they used to. The growing season, as we saw in the last presentation, is getting longer. And so a big question is, can we see evidence of this? A recent paper by Sweeney et al. Says no. They find no evidence of changing emissions at Barrow over 29 years. And this is based on what they call a sector analysis, which seeks to compare background air at Barrow from the clean air sector with air coming from the nearby wetlands and the town of Barrow and the gas wells and all that. So what you see on the bottom figure in the left is how different the seasonal cycle is. When you look at the clean air sector, you see a very nice seasonal cycle with a minimum in the summer, just like all the other background sites. But if you start looking at air that might be coming from the nearby sources, you get a pretty strong growing season peak. So the question was, you know, can we see evidence that the size of this peak is changing over time? And even though temperature has been changing very rapidly in this part of the Arctic over the past decades, there's no statistically significant trend according to this sector analysis. And there's another paper out that disagrees with this. They find that there is evidence of changing Arctic emissions, and they do this using the amplitude of the seasonal cycle. So you might imagine that if wetland emissions are increasing over time, the summertime minimum might not be as deep as it used to be because wetland emissions are maybe filling in some of the seasonal cycle. And they find a significant trend in the seasonal cycle at Barrow, but not, interestingly, at other background sites, which are perhaps too far away from wetland sources to actually pick up any kind of signal at all. So this is very interesting. The problem is, of course, that it's not just the Arctic that's changing. Emissions all over the world are changing, and those signals are being transported into the Arctic. So it's not clear how robust this result is in terms of, you know, what it may say about nearby wetland emissions. And finally, Katie Walter has a paper out where she's tried to estimate how much Arctic lakes have increased emissions by just due to permafrost thaw, and finds, in terms of yearly emissions, a very small effect. So my last slide is my comments. I think when we try to detect changes in Arctic emissions, you know, we're looking at a very small piece of the global methane budget. And we have a lot of atmospheric variability, and we have trends in much larger sources at lower latitudes. We are really trying to find a very small signal. To see a small signal in a noisy system, we need sustained observations of all types, fluxes, atmospheric concentrations, and we need adequate spatial We need adequate spatial coverage. I'm sorry, Roshan, your comment here has distracted me. I would say yes, Barlow does contradict Sweeney et al. And then finally, if we really want to understand what's going on in the Arctic, we cannot limit our attention to just the Arctic. We really have to know what's going on with the global methane budget. And we have to have good estimates of anthropogenic emissions, for example, and how they're changing over time. And I'll end there.
Can you hear me?
Yeah.
Thank you so much, Lori. It's been a fascinating talk, and you pointed out the area where we really need information beyond the Arctic. In any case, this is fascinating. I think we probably have time for a question or two if some of you on mute want to participate.
Hi, this is Chip Miller from JPL.
Hi, Chip.
Lori, I have a comment. Hi. A comment. When you're doing your perusal of the literature and assembling your bottom-up inventory estimates, there's a great deal of double and triple counting when you're collecting those papers together. So the actual numbers aren't quite as high as 75 or 80 teragrams per year. It's more in the 40 to 50 teragrams per year range, but it's still, as you correctly point out, the bottom-up scaling still seems to be about 2x of what the atmospheric observations would support.
Yes, thanks for mentioning that, Chip. I really should have had that on my slide with the scaling up. It's true. There's definitely a lot of double counting, and it's hard to know. I'd be interested in hearing how you arrive at the 40 to 50 teragram number. Is there a publication where people have tried to account for the double counting?
In some of the stuff that we've done with the CARV data and then talking with others and also the inversions that Scott Miller has been leading, it seems that the atmospheric inversions are coming in at about 40 to 50% of the priors.
Okay. Well, that's interesting. And well, there's also some anthropogenic emissions entering into it too. So my bottom-up numbers did not include anthropogenic either. And there's not as much anthropogenic emissions as other parts of the world, but it's still something also that adds in there.
Hi, this is Dave Douglas. I was wondering about that about 10-year hiatus in the time series around the 2000s in the global increase in methane. Are there speculations about what caused that?
Yeah, I didn't get into that. So in addition to wondering why the recent global methane is going up, another associated question is why did it level off in the first place? And people have proposed various reasons why that might be. It's been proposed that wetlands leveled off, and we're talking again about the tropics. You know, the tropics might be getting drier, so perhaps there was less wetland emissions. Other people have suggested that oil and gas emissions decreased as the industry became more efficient. But I would point out that it's not necessary to have a decrease in a source to get that kind of behavior, because unlike CO2, which just goes up as long as we keep putting fossil fuel emissions into the atmosphere, methane can reach a chemical equilibrium because it has a loss rate that's about equal to the global emissions. So eventually it will level off just because it's coming into chemical equilibrium. But recently something has started to change again, and that could be that the global sink has decreased for some reason, or emissions are changing, or some combination of those.
Thank you.
Okay, I want to thank both sets of presenters for some really fascinating talks. You've really, I think, contributed to us all. And I can't see the attendees, but I hope there are some interested folks beyond the atmosphere team on the call.
So I'm going to talk about some work that I've been engaged in with Ed Dlugokenski here at NOAA, Ezerol in Boulder. And what I'm going to talk about is the state of our knowledge about the atmospheric budget of methane in the Arctic. And I want to start out by showing one of our products that we have here at NOAA GMD. It's called the Annual Greenhouse Gas Index, and it's entirely based on observations of trace species that we make using our global network. And we calculate the contribution of different greenhouse gases that have significant anthropogenic components to their budgets. And we ask ourselves, how has the forcing of the climate changed over time as emissions have gone up? And this figure shows very clearly that when it comes to radiative forcing, handle on how this pie gets divvied up. Recently, global methane observations have shown that methane, after appearing to level off in the late 1990s and early 2000s, is now on the rise again. And at first, of course, we were hoping that maybe it would be just natural variability. Maybe we just had an extremely warm and wet year, especially in the tropics where most of the emissions are in the end. But no, it's sustained, and it's continuing to rise. So an important question, of course, is what is driving this recent growth? Is it anthropogenic or natural? And in terms of this question, many things have been proposed. Some people have suggested that the Arctic is actually responsible. Others have suggested that it's related to the explosion review article that appeared last year by Ted Schur et al. And there are some revised estimates of how much carbon really is thought to be locked up in frozen Arctic soils. And it's quite a huge amount, 1,300 to almost 1,600 petagrams of carbon. Estimates are that 5 to 15% of this could become vulnerable to being emitted to the atmosphere as greenhouse gases, CO2 and methane during the century. But the current thinking is that this release will be gradual. It'll occur over multiple centuries rather than being a sudden catastrophic burst, which leads us to understand that if somehow the global society is able to get their act together and control emissions of carbon and keep the global temperature increase to less than about 2 degrees, perhaps we'll escape the worst effects of the carbon permafrost feedback. So now, the thing about methane is we don't really understand the global methane budget very much. There's many different versions of the global methane budget. I'm showing you this one because I happen to think it's really kind of an artistic representation. But you'll find some budgets that evenly split emissions between natural sources and anthropogenic sources. This one happens to have a little bit larger natural sources than anthropogenic. But it's really difficult for us to divide up this pie into different emission processes because, well, a lot of the emissions are very spatially overlapping or very diffuse. It turns out to be pretty hard to get a good CO2 is really the big story. But the second largest contributor is methane. So we definitely want to understand methane. And understand its budget and how its emissions may be changing over time. An interesting thing about methane is that when it comes to the Arctic, methane is quite a climate-forcing bogeyman. There's several processes that have received a lot of attention that allege that there could be huge climate feedbacks coming from changes in methane emissions, especially in the Arctic. And here I have a slide describing the permafrost carbon feedback. I'm not going to discuss the potential release of large amounts of methane from ocean hydrates, but that is another issue that people have looked at. In terms of the permafrost carbon feedback, there was an excellent